What I do when we have to like
Hello, everyone. Sorry for the delay. Welcome to the September BERG Seminar. For those joining us for the first time, welcome, and to everyone else, welcome back. Those who don't know me, I'm Matt Lee, Research Associate in the school. I work in-use building performance metrics. But BERG seminars aren't about me. BERG seminars are about getting everyone in the Building Energy Research Group together in person to give us a chance to engage with each other face to face. And we're also allowing us to hear from a wide variety of speakers, both from inside and outside of BERG. And that covers inside the department and within Loughborough University, and also speakers from outside of Loughborough. Get to hear a wide variety of speakers talking about working topics relevant to the work that we do in the Building Energy Research Group. Today's speaker is Dr. Ben Roberts. I'd like to join me in welcoming Ben and thank him for his time today. Ben is a research fellow in the Building Energy Research Group here at Loughborough University. He's got extensive expertise in measuring thermal comfort and indoor air quality, and is researching how buildings can provide comfort, health, and well-being in temperate and tropical climates. So, welcome, Ben, and please take it away.
Okay, thank you, Matt, and welcome everyone. Yes, so my name's Dr. Ben Roberts, and I'll be talking about some of the work I've been doing over the last 2 years in the group. So extreme heat kills 500,000 people every year, and 1 billion people have to work in extreme heat conditions. So it's a really serious issue and a research area that I'm really passionate about. So just a quick background on me. I joined Loughborough 8 years ago. I was part of the CDT, similar to IRBI. It was the precursor to IRBI, which we're all part of today. But prior to that, I did my first degree was actually in geography. I don't come from a hard engineering background. And then I first got interested in energy with an energy policy master's, also at Exeter. And then since then, I've been at Loughborough doing my MRes, my PhD. And then since 2019, I've been a research associate working on 4 different projects. And it's REFIT, which is the one I'll focus on today. That's the first project that got me involved into doing research in tropical climates. And then this year, I've just started my fellowship, my doctoral prize fellowship, which is all about doing research in tropical climates. But just to identify a few of the key collaborators, I'll probably mention these names today, so I thought it's best to talk about them up front. We've got Professor Kate Goff from Loughborough University, Department of Geography. She's someone who's really influenced my career in the last 2 years. She's been working in Ghana for over 30 years, and she has set up 2 recent projects. She's actually a social scientist herself, but has become really interested in the way that people experience heat in their homes. And she's very interested in how people who have home-based enterprises, how they work under extreme heat conditions. We've got some excellent colleagues out in Ghana as well, at the University of Ghana and University of Development Studies. And also, of course, Professor Kevin Lomas, who is here in the Building Energy Research Group, always giving me great advice about building designs for tropical climates. So the structure of my presentation today will be quite a linear one, following through the projects that we've been undertaking over the last 2 years that I've been involved, and further back 4 years. So I'll talk first about VUEC. This was the Vulnerability to Extreme Weather Events in Cities project. And this was a partnership between Loughborough University in the UK and the University of Ghana and University of Development Studies out in Tamale. So what they wanted to do was focus on both extreme heat and flooding to examine how extreme weather events, heat and flooding, affected water, health, electricity services and also income generation with a specific focus on the urban poor. And then they wanted to start looking at ways of like adaptive strategies to these extreme weather events, and they didn't quite get there. And that's where Refit, which is the next project, comes in. So I'll be talking today purely about our research in Ghana. For those of you who perhaps aren't aware, it's a country in West Africa. There's the three largest cities. We work in two of those. We work in Accra, which is this city right in the south of the country, the capital, by the coast. It's very warm most of the year, but very, very humid. So I've been there when it's been probably late 20s, early 30 degrees, but around 80–90% humidity. So really hot and humid, very uncomfortable to be in. The second city we work in is up in Tamale in the north of the country. This is very different. The heat is a lot higher. We've been there when there's been 42, 43 degree weather, but the humidity tends to be quite low, around 10 or 20%. So actually, I find Tamale much more comfortable to be in because you can evaporate your sweat and cool down despite the much higher temperatures. We know that climate change is going to be a significant issue for the whole of the African continent, and it's there will be asymmetric warming, particularly along the African continent. And in Ghana alone, about a quarter of the population is identified as poor. So these people are particularly vulnerable to high indoor temperatures and heat because they can't afford things like air conditioning and they don't have a reliable electricity supply for cooling systems. We at the moment almost universally work in informal settlements. So this is an example of an informal settlement that we work in Accra. This is called Ababloshi, which is famous for the world's largest electronic waste dump. So a lot of the electronics that you throw away, if they're not properly recycled, end up right next to this settlement. And informal settlements are places where the urban poor live. They tend to be not government approved settlements. So at any point, the government can come in and destroy all the homes in this area. And so people tend not to want to make massive investments in their living environment. And also people just don't have much money, so they can't make a lot of improvements to their homes in terms of adapting them and retrofitting them to make them more resilient to extreme heat. So the previous project, it looked at indoor temperatures, so air temperatures, dry bulb temperatures only. I know I've just mentioned about the importance of humidity, but the early project just looked at temperatures. And working across the two cities, Accra and Tamale, they monitored indoor temperatures in almost 130 homes using these very small, tiny tag sensors. They're waterproof. They have quite a good battery life. They're quite strong and tough, so they're quite a good solution for monitoring temperatures in this kind of environment. And they sampled a number of homes which encompass different building types, different materials. So, for example, a thatched roof, a tin roof, wooden walled houses, concrete walled houses, houses that were under shade of trees, houses that were exposed, and started to compare the temperatures that were recorded in all these homes. And what was quite shocking is some of the temperatures recorded were very high. So the highest temperature here, 45.5 degrees. This is a living room. It's right next door to a bakery, which probably contributes to some of the heat. So the oven is in a big room next door with this living room attached. And they bake bread all night long, which is the time when about 8 or 12 women sleep in this room with their young children. It's otherwise quite poorly ventilated. You can see this small window here. That's the only ventilation in that house. And you think 8 or 12 adult women plus children sleeping in there. It's quite uncomfortable. So one of the key comparisons that was made was the effect of roof material on the indoor temperature. And they contrasted thatched roof dwellings with metal roof dwellings. So on the x-axis we have time, and on the y-axis we have temperature. The dark solid black line, that's the outdoor dry bulb temperature. And then the brown lines on this graph here, they're the indoor temperatures in all the houses with thatched roofs. And on the right-hand side, we have the indoor temperatures in all the houses with metal roofs. And what you can see is that the thatched roof, the indoor temperatures were generally quite stable. So they didn't fall very far off in the night, but equally they didn't shoot up during the day. You contrast this with the metal roof, massive increases in temperatures during the day, but actually comparatively lower temperature at night. So what we can say from this is if you want to spend your time in a room during the day, go in a room with a thatched roof. If you want to sleep in a room, choose a metal roof. Unfortunately, most of the rooms in the settlements that we work in are multi-purpose rooms. They're living rooms and sleeping rooms and cooking rooms and very often workplaces as well. So there's always a balance between the design of the building and the temperatures and the time of the day. So we haven't solved this problem just yet. Unfortunately, people are moving away from thatched roofs despite us showing that they are generally cooler during the day. So they're becoming, they're not culturally acceptable in many of the people who have told us in the settlements. This is partly because they're a fire risk. They harbour insects and snakes and lizards. The thatch is not necessarily grown close to where the houses are. The local craftspeople who used to make the roofs are moving away, or they're losing the skills. People much prefer tin roofs. They're cheaper, they're easy to install, and that's a sign of modernity. So unfortunately, what we see is a movement away from the thatch, which perhaps is a better solution in terms of extreme heat, towards metal roofs. And so VUEC was all about identifying the problems, and REFIT was, which is the project that I'm involved in, is about solving some of these problems, improving building design. So it's called REFIT, which is reducing the impact of extreme heat to improve well-being in cities. Once again, the core team of Loughborough, University of Ghana, University of Development Studies were involved. And then we also brought in the Council for Scientific and Industrial Research, Ghana. They had building consultants who advised on the project. And also Kevin, Effie and I were brought in as the engineers, architects on the team to help inform the building design. And the main aim was to co-develop. So that's develop in combination with the people who actually live in these informal settlements, not us just to come in and say, you should do this, we think this is the way to do it, but to co-develop low-cost, affordable interventions for retrofitting the informal dwellings and workplaces in culturally sensitive ways. It must be done in a culturally sensitive way, otherwise people aren't going to want to do this and make these changes to their homes. And the ultimate aim is obviously to reduce heat stress and improve well-being for the people who live there. Just got a couple of photos here. This was back in February 2020, my first ever trip out to Ghana, right before the COVID pandemic. So at this point I think when I was out there, the stock market had just crashed and someone said, oh, that's a bit strange. We didn't really know anything more than that, but yeah, so that was an interesting time. So this is on the right-hand side, we have our Accra team. On the left-hand side, we have the Tamale team with our advisory boards. So in both locations, we have an advisory board of local architects and government officials. We have someone who designs the building regulations for Ghana. We have people who work in hospitals and healthcare advisors to advise us on the project. We're now working in just 4 settlements, not the 8 as in VUEC. So we have Alajo and Abagloshi in Accra and Kukuo and Lamashegu in Tamale. They're reasonably similar, the 4 settlements, but obviously they are different in terms of their location. So the Tamale ones, higher temperature, low humidity. The Accra ones, lower temperatures but high humidity. And the Accra dwellings tend to be built of wood. They have wooden walls. And in Tamale, it's much more common to have really thick concrete or sandcrete or mud walls. So this was the first time we went to Ghana. This was like Paul. I know Paul Draw is on the team's call. Got out of the car and we walked into our first house. And usually, if you've ever played with an IR camera, you always go, "Oh look, my hand's white and glowing, really hot." He said, "Oh my God, my hand's the coldest bit in the room." So we were recording roof temperatures much higher than this, 60 odd degrees in some places. And his hand was the coldest bit. And that was kind of our introduction to extreme heat in these kind of dwellings. So this was just a thin layer of metal exposed to the sun all day, beating down. You can imagine how uncomfortable it was to be that far away from a 50-degree surface. Really, really uncomfortable. So for the refit project, we had the following research questions, which then map onto our methods. We want to know, how do people perceive indoor temperatures? What building adaptations could reduce indoor temperatures? And then how effective are these building adaptations at reducing indoor temperatures? So to answer research question 1 about how do people perceive the indoor temperatures, we use something called a thermal comfort survey, which some of you may be familiar with. Early students, you'll become very familiar with this over the next few months, I'm sure. And what we have done here, we've completed 160 surveys over 2 years, picking up warm parts, the dry season and the rainy season over a 2-year period. And we go into people's workplaces or their houses, and we ask them a number of questions. But the main question we want to know is, we say, how do you feel right now? How do you feel in this environment in terms of temperature? And they answer on this scale from neutral up to hot, down to cold. And at the same time, we take a note of what they're wearing, because obviously the clothing that you wear influences your body's ability to lose heat to the environment. We also ask what the person's currently doing. So for example, this lady here, she is a seamstress. So she's sewing and she's cutting things and walking around her shop. And her body's obviously heating up. Someone who's just laying around in bed or sitting around have a much lower metabolic rate, and so their they'll feel cooler potentially. At the same time as doing that, you'll see my hand here. We measure some other variables. So we measure the air temperature, the radiant temperature of the room. So that's picking up the temperature of all the surfaces around the person. We measure the relative humidity. I've talked briefly about why that's so important, particularly it prevents or allows your body to evaporate sweat off the skin surface and cool you. And we also measure the air velocity, and this impacts the way the air moves across your skin to help evaporate sweat and convective cooling. So we measure all these things objectively. We also have the subjective measurements of thermal comfort, and we combine them and we find how a variety of different people under a variety of different thermal conditions perceive that thermal environment. And that then allows us to design buildings according to their thermal comfort preferences. So if we find that people are comfortable at a certain temperature, we can try and aim for that with our building designs. The other thing we've done to answer research question 1 is, how do people perceive indoor temperatures? Well, the seamstress, she may well be in her room all day sewing, but other people are in and out of their room all day. Perhaps the room's just too hot for them to be in. So there's no point us going into their room and doing a comfort survey, because they're going here, there and everywhere, sitting under a shady tree to cool off. So if we're trying to find out the actual temperature that people experience. And this is quite a hard thing to do, because what we did is we put these small sensors, these are eye button sensors, very small, very lightweight sensors. And we asked people to wear them either around their neck or on their wrist, using a special mount that we designed. But of course, it's quite close to the body. And so then, therefore, you're getting the interaction of the body's heat with the sensor. So it's kind of a method that we're developing and then exploring. But we've got some fairly interesting results because we've combined it with diaries, and that's probably the more interesting thing. So just to look at some temperatures, some temperature profiles. So again, we have time along the bottom, temperature up at the side. So the orange, the yellow line here, that's the outdoor temperature close to the person's room. The red line here, that's the temperature inside their room, recorded on one of those little yellow time tags. Then the blue and the grey line, they're the temperatures we recorded on the person's body. And it's quite interesting to see that often there's a big deviation. So for example, this person, their workshop temperature is actually quite high compared to what they were experiencing. And then we used the diary, and the diary, he said, well, I'm a night watchman. I work in the evenings, I'm not in the room, I'm sitting outside. So he was experiencing a much lower temperature than we were actually assuming if we said, okay, he's in his room. You can also see there's other strange points where the temperature goes much higher than what he's actually experiencing. Perhaps he's gone for a walk outside, he's had to go to the local market. And that's the kind of thing that we picked up on with this diary. It was a WhatsApp diary. So whenever the person did something different or went somewhere, they WhatsApped one of the research team, and obviously then we had the time and we had what they said. So here's some examples. I'm at the shop, I'm doing some ironing. So we know ironing produces heat, so we could potentially look for that in the temperature profile. And then he says, okay, at 1:34, I'm going out. So you know he's then left his house. He's given us a lot of information about he's walking in the sun, about the temperature. And we had this for, I think we had about 12 people did these diaries. It's quite a lot of data to analyze with all these diaries and the temperatures. So we haven't got much further than this yet, but as a group, we've learned some interesting things. Also, methodologically, this is the first time we tried out this neck sensor, wrist sensor. And some people were saying, okay, well, I don't like wearing the wrist sensor because I'm trying to wash my clothes and I keep having to take it off and put it back on. It's getting wet. But down in Accra, in the capital, people were saying, well, I don't like this sensor on my neck. People keep coming and asking me what it is. They much preferred a sensor which looked more like a watch on their wrist. So there's just a few interesting things that we'd think about for future studies. We also need to think about the difference between the temperature recorded on the wrist and the neck. And we've done a few pilots where we had people wearing both sensors at the same time to try and see if there was any difference in temperature. But this is really multidisciplinary research. We're not only doing the engineering and architecture side, measuring temperatures, we're also asking people using photo voice interviews. What we did here was either one member of the research team followed a person around for a day, or we gave someone a camera and they went around about their daily activities and took photos of things. For example, this is a place where I feel hot, or this is a place where I feel cool and comfortable. And then we went back and interviewed the people using the photos they'd taken as a prompt, and they'd tell us about the photos they'd taken, about their experiences, about how they felt. We asked people to take photos of like specific building materials that they liked or disliked. But it was again a very useful experience. And during these interviews, we also asked people questions about the acceptability of the different interventions we might propose, such as what if we changed your ceiling insulation? We've seen in some houses people started to put plastic bags suspended on nets above their ceilings. So would that be something that would be acceptable to them? Could we plant trees around your house? Well, speaking to people in Tamley, they wouldn't plant a tree themselves because they say if you plant a tree, you won't live long enough to see the tree bear fruit. So their belief is that if you plant a tree, you'll die before it's mature. And so there's no point us going, well, you should plant these trees and shade your houses if it's a culturally unacceptable thing to do. Whereas down in Accra, they have slightly different beliefs, but they there say, well, I don't want bugs and lizards and insects in the trees around my house. So again, tree shading is quite an unacceptable thing for a lot of people. We also asked about different feasibility issues and how much people would be willing to spend, because obviously we can't suggest something which is so unbelievably expensive that people can't afford it. So back onto more of the engineering architecture side, we have built some experimental buildings, and we've constructed these to compare the effect of different material types, ventilation and shading on indoor temperatures. So this is the method we use. It's a match pair method, which NASA have also used. So NASA got a pair of twins who were physiologically almost identical. They sent one up to space, kept one on Earth, and they brought the one back down from space and compared their weight, their muscle mass, and saw how they changed. And basically, the intervention there was that one was in space and one was on Earth. We've used exactly the same method, but instead of sending these houses into space, we're going to change the roof type or change the ventilation type, always keeping one house on Earth. So one house will always be the same. It will be our control house, which we then always compare back to. And the thing we compare is the indoor temperature. We measure the indoor temperature in all 4 houses, keep one house the same, change the roof type on one, and the other maybe change the roof to a thatched roof, and the other house maybe an insulated roof, and then compare it back to that original house under the same weather conditions, and we can see the effect of that intervention on the temperature. The first stage of informing our design, which relates back to research question 2, what building adaptations could reduce indoor temperatures, was about we used dynamic thermal simulation to design our building. So instead of building these 4 test houses and scrabbling around trying to decide what we did, we tried lots of different things, lots of different roof types, lots of different wall types. It gave us the opportunity to do it very cheaply and very quickly, to see which was the best option, best retrofit to cool the dwellings. And what we found was having a really highly ventilated roof structure with then an insulated roof ceiling underneath was one of the best options for keeping the indoor room cool, both day and night. The thatched roof, which I keep coming back to, was also quite an effective measure. So from there, we took what we'd learned with the dynamic thermal simulation and drew up some plans for the 4 houses. And we discussed this with the wire team, with the advisory board. Here's the local builders. We were saying to them, is this feasible? Is this what you would usually build in the communities? Because we wanted something which was close to what they actually use in the communities, because then when we make our retrofits, it seems reasonable and believable. So back almost a year ago, we broke ground on the test, on the experimental buildings. And then here's some photos of them laying out the foundations. The houses the front door faces south on all 4 houses, and it was pretty much perfect based on the compass. And we chose to build the house out of sandcrete blocks. And sandcrete blocks are a mix of sand, cement, and water. And they mix it on the ground, put it into stainless steel metal molds, compress it down, and then just tip the block out. And it took them about a day and a half to make 600 blocks. And they're all laid out and they dry in the sun in about a day. We chose sandcrete blocks because that's what most of the people in the communities we work with were building their houses out of. So we didn't want to start with our base case houses as something crazy. We wanted to stick with what they were using. So here they are, dry within 1 day. We're able to stand on them. So the guy on the left, he was the mason, the sort of the site manager. He was in charge. Then we have Kate Goff, Professor Raymond, and then our research assistant Abdullah, and then me, obviously. We then had to go and choose the roofing material for the base case houses, so for all 4 houses. And everyone's using this tin now. This is what everyone likes to use. But it's so thin, it's very, very light. You can almost bend it with your hands. It's not like if you ever go down to B&Q or Wickes, the stuff we get in the UK, much thicker. It's very, very thin and lightweight. And because of that, when the sun hits it, you get almost immediate transmission of heat through it. In the future, what we'll do is, so you can see this, the mason here is blocking up the gable end. In the future, we may take that out again, put a ceiling underneath, and then have a really well ventilated roof space. We've also got plans to obviously change the roof type. We'll put a thatch roof on one of them and increase the ventilation openings. So there's going to be vents at all different parts of the house at different heights, and see how that affects the indoor temperature. Again, with the sense of realism, we put both burglar wire and mosquito mesh on the houses, because obviously this is a malaria zone, so that's what people will use, but it does restrict the ventilation, obviously. So this is the alternative roof design. This was kind of our, okay, it may not be culturally acceptable, affordable, but it's probably one of the best options for cooling the house. So let's see if we could do something quite innovative and interesting. So this is, there's a hole at the full length of the ridge, which allows air to hopefully move up through and out of the chimney exhaust system whilst blocking the rain off. Yeah, a few people have expressed issues about this in Ghana to do with bats entering and birds entering, and it being a source, potential mosquito entry point. So it's by far the coolest of the 4 houses already, but perhaps not culturally acceptable and quite difficult to build. The builders had a lot of trouble building this. So, you know, plenty to think about here. So inside the house, we used some battery-powered sensors to measure the air temperature. We also measured the roof temperature, the floor, the temperature of the walls, and we did that with battery-powered sensors because we didn't have any power to the house at the time. It was the quickest, cheapest solution. And then we also measure weather on site. And here's a bit of data from the first test we did. So all 4 houses operated identically. And we were pleased to see that the measured indoor temperatures in all 4 houses were very similar. What we didn't want to see was one of the houses having a much higher temperature or a much lower temperature, because when we've come back to compare the 4 houses, what we want to do is say, okay, the temperature difference in house 2 is purely down to the intervention made. It's not because there's some other defect with the house. So this was a good sign for us. Okay. So just now to talk about my most recent work, my fellowship. The VUET project did a little bit of monitoring in hospitals. And what they found was that extreme heat affects patient well-being and recovery. So the place where you go to try and get better, hospital, is not necessarily the ideal place if it's exposed to really high indoor temperatures. And the hospitals are most crowded when it's hot. So people are getting ill in their homes, all going into hospital, which is becoming more and more overcrowded, more and more hot. If people have got open wounds and they sweat because they're too hot, that can cause infections. And there's also records in these hospitals of people sleeping outdoors. So they've been admitted to hospital, but because it's so hot, they then go and sleep outside and are exposed to mosquitoes, which potentially leads to malaria. The hospitals don't like to rely on air conditioning because the power supply, at least in the northern part of Ghana, is quite intermittent. So you can't rely on air conditioning to provide cooling when you need it. And we also need to think about the staff, not just the patients, because they're the ones who are running around, getting warm, lifting people up, and also wearing PPE, which increases your sensation of being hot. We are aware from a lot of the literature shows that newborn babies and pregnant women are particularly vulnerable to extreme heat. And it was back in 2020 when I first went to this hospital and I was taken into the newborn intensive care unit, and I had a temperature sensor in my hand and it was 35 degrees inside this intensive care unit. And obviously you've got the most vulnerable people in this very, very warm space. So it's a real health issue. And I thought, okay, we're not addressing this on refit, but for my fellowship, this is where I wanted to come and base my research. One of the things we noticed in this hospital is that there's potentially some good options for ventilation, and ventilative cooling. There's some holes in the roof, but some of them were blocked, and it was a bit confusing. Clearly, someone had designed the building to be quite well ventilated, but perhaps the building wasn't currently being operated in the most efficient way. And I was there at this hospital back in June, and I was told that this used to be a school, and then it was converted to a hospital. So perhaps during the change of use, that's when some issues cropped up. I've also got some modern hospitals that I work with. This hospital was built in the 1970s and then later extended. And the trend in modern buildings in Ghana tends to be to use sliding windows. And these are a bit of a problem because if you can imagine, had this have been a louver window, so blades of glass which tilt up, you could have had this full area would have been an open area. But with a sliding window, you only get 50% of the window open area available for ventilation. And so because of that, they have to install air conditioning. Now, that's when I became interested in indoor air quality. So I did some work in 2021 on the events research programs. This was a government initiative to reopen mass gathering events after the COVID-19 pandemic. And I was involved in the field trial. You can actually see one of our sensors right down in this bottom corner in one of these press shots. This is the Download Festival just up the road in Castle Donington. And so I became very interested in air quality, learned about the different methods that we could use to collect and analyze data. And then I incorporated this into my fellowship, which my fellowship is now trying to deal with both low and zero energy cooling, so keeping hospitals cool without using air conditioning, whilst providing good indoor air quality to dilute airborne viruses and prevent mosquito-borne diseases, so stop mosquitoes entering. So you can't just have huge holes in the wall, which may well provide cooling and dilution of airborne viruses because mosquitoes will come in. You can't tighten it all up to stop mosquitoes coming because then you probably can't cool it and you can't dilute your airborne viruses. So it's kind of a three-way problem to solve. And the work I did in June, the data I collected in June, I've just written up into a conference paper, which I'll be presenting next week at the AIVC conference. And what I'm focusing on is, okay, if you put air conditioning in a hospital to keep it cool and provide thermal comfort, how does this affect the indoor air quality? So I've got 4 hospitals in my sample, but for this paper, I just focused on 2 of the hospitals, just to initially see if the air quality was satisfactory, where it could be improved. And I've got Children's Hospital down in Accra, and then the Tamale Hospital up in Tamale. Most of the wards tend to be naturally ventilated. Here's the louver blades that I was talking about earlier, the tilting glass blades. In one ward, in the other one, you've got tilting windows, and this one you've got sliding windows. So there's a real mix of ventilation options. But notice this here, this is a recirculating air conditioner. So this provides cooling without introducing fresh, uncontaminated air to the space. And this is where the problems start to arise. So we're obviously all aware of the issue we've faced over the last 2 years with the pandemic. We believe the way that the SARS-CoV-2 virus is transmitted between individuals is primarily via the airborne route, either droplets, so larger virus-laden droplets which fall to the floor quite quickly, or smaller particles, virus-laden aerosols, which are so small they float around in the air and can potentially be breathed in by someone else and the infection transmitted. So we're concerned with this study about the long-range aerosol transmission. Now, the aerosols are emitted when people are breathing in and out. Something else happens when you breathe in and out. You breathe out carbon dioxide. And if we can measure the carbon dioxide concentration in a room, we can understand people's exposure to exhaled breath, which may or may not be contaminated with virus-laden aerosols. So I used some small CO2 sensors. I've got one of them here, quite unobtrusive, battery-powered, logging to the device sensors. mounted them in 4 different hospitals, and logged the CO2 concentration alongside temperature and humidity. And you can see a few of the sensors in place. I tried to put them in discrete places where kids weren't going to go and play with them. At the same time, I wanted to be able to measure the CO2 concentration in the room, so I couldn't shove them away in a corner. I also talked to the staff and trained local PhD students how to use the equipment. So very open about what we're trying to do, and very forthcoming with the knowledge that we were gaining. And this is what we want to do. We want to keep CO2 concentration below 950 parts per million. That's our aim in these spaces. I've been logging data since June, but I've just selected a small component for my my conference paper. So during the monitoring period, the temperatures were quite cool, people were telling me. So 28, 29 degrees. We probably wouldn't consider that cool, but in Accra and Tamale, they said it was cool. So that perhaps influences how people were using the ventilation systems, opening, closing windows. We'll see if it changes as the year goes on. So remember that 950 parts per million, we want to keep it below this. And most spaces in both of the 2 hospitals, the air quality was satisfactory. It was below that 950 parts per million target. You can see a few of the wards, there was a few issues. And the thing they all had in common, these were the wards with recirculating air conditioning, where people would close the windows, turn on the air conditioning, restrict all the ventilation. Here's the Pediatrics Ward, which I showed you earlier. What was happening was the parents in the ward were telling the staff to close the windows because their children were cold. You were then getting a buildup of CO2, and overnight, to stop mosquito entry, so mosquitoes are most active during the night, they were just using the air conditioning for comfort, to provide comfort. At 6 o'clock in the morning, the windows were all opened and the CO2 level dropped. So what this shows is that the fact that the ventilation wasn't operated properly, or there wasn't enough fresh and uncontaminated outdoor air allowed to enter, that potentially increased the risk of airborne virus transmission. Saw the same thing with another ward. This ward was almost fully enclosed. There were other wards around it, so really not much of an option to ventilate this space. Very small windows, tucked behind beds, so really hard to open, and consistently high CO2 concentrations were recorded in this space. So compare this to outdoors, about 450 parts per million, indoors up to 3,000 parts per million, which really is quite a worrying sign of the quality of the indoor air. So whilst the air quality was satisfactory in most spaces, it was the air-conditioned wards which were at high risk of poor indoor air quality. And it's from the other drivers, thermal comfort and mosquitoes, are driving this ventilation, this choice of ventilation and impacting the air quality. So yeah, please, if you'd like to read the paper, just drop me an email. I'm happy to share it. My colleague who works at University of Ghana has also just won a fellowship, and he's working in schools. So what's quite good is that as a group, we're now covering houses, schools and hospitals. Schools are quite different from hospitals because obviously they are only occupied during the day. And this one is particularly a particular issue because it's got a metal roof. So remember, we talked about how a thatched roof is the best thing during the day because you don't want the solar radiation being transmitted through warming up the surface. For a school where people are only there during the day, a tin roof is probably the worst design you could have chosen. But that's just started as well, so there's more work to be doing there. Just to finish, really, I'll just talk about some of the methods and some of the learnings that we've taken from it. One of the things we do is we employ community champions, and these are people which are nominated by the communities themselves. They're representatives of the communities. Whenever we go and visit the communities, we first of all go and meet the champion. They show us around, and they're kind of our are representative whenever we're there. But they're really useful because if there's any issues with any sensors, they can quickly go and check it. They help us to build trust in the communities, and they're really keen to get involved in the research as well. So it's really good to work with them. It's really important to develop and maintain relationships because we're going into people's homes, and it can be quite intrusive for someone just to walk in and start asking you questions about how you feel about your comfort and, or have you thought about changing your roof? So we keep going back. We go back at least every 6 months, talk to the people, spend a long time with them. The thermal comfort survey might be 10 minutes long, but we might spend 45 minutes just talking to the people about, you know, what's been going on in their life. And because of that, we're also really grateful for the people who are participating in our research. We don't pay them, so they're just involved because of their own interest. But at Christmas, we do give everyone a bag of rice, just as a kind of token of our appreciation. It's really important to build capacity within the local universities. So we train local researchers, and this has been really useful because during the pandemic, I couldn't go over there and travel. So these guys were collecting all the data, which was really, really useful, and give feedback to the people who need it. So there's no point us academics holding on to all the data and all the knowledge. We need to give the data back to the people who are living in these homes and advising them about what we see and how they can improve their indoor environment. So every single household got one of these when we last visited. We've obviously got a lot of benefits from working together. The team is now really highly trained, and we as UK researchers have learned so much and are still learning about doing research in tropical climates and how the culture of Ghana influences the ways of building and cooling. So the future will be another fellowship for me. Hopefully, we've got some more grants going in. I hope if any of you are interested, you'll consider doing PhDs in the area. I've got some ideas, and if you've got some ideas, please approach me. And that's it. Thanks for listening.
Thank you very much, Ben. So let's open up to the floor for questions now. It's okay with you, Ben?
Yeah, sure.
So as part of your refit scheme, you mentioned you built control homes with some of the local sort of materials, resources. Were people actually living in them while you were testing them?
No, they were unoccupied, because if people are living in them, they might do things we don't want them to do, such as opening doors, opening windows, cooking, producing heat. So they were unoccupied, all four.
My question then goes on to say, because you kind of cut out all the living sort of heat and human heat, does that mean your data is no longer a direct comparison of, well, this is better than what you're living in currently, because you haven't actually tested what it would be like if they were living in these new homes?
Well, the heat from a human body is probably 100 watts, 70 watts when sleeping. So compared to the kind of gains we're getting from the incoming solar radiation completely wipes out any influence of humans. So the heat coming off a human body is relatively small compared to the other heat sources. But for the purposes of this, it was much more important to have the houses otherwise identical than to have an extra 100, 200 watts of heat input. But we have got power supply now. We could put some heaters in there. It would raise the temperature slightly. But because none of them have got any occupant supplied heat, then we can still make direct comparisons.
Thank you. Questions?
Ivan, thanks for the presentation. My question is related again to the identical form. I was wondering, like, is external shading and cool roofs are one of the options you are trying to explore there? Is it?
Yeah, that will be one of the things we move on to. Yeah, so we purposely went for very small overhangs initially, because then we can add larger and larger ones on. So we'll put overhangs. We're thinking of either changing the roof type or color, or even trying to paint the roof, something that someone can do fairly cheaply.
Did this project in reality have any impact? Like, do you have a chance to build these homes future by the government or anybody?
Yes, so the next project, we've just applied for a new grant, and if we get that, we'll retrofit 400 homes. So if we get that, we'll start having some impact. Yeah.
Regards to the design of these sample prototypes,
Mhm.
what was the reaction of the local population? Were they comfortable with the idea of relatively confined space with a slightly different design than they were accustomed to?
Yeah, so the floor plan, the actual size was taken as we did a survey of the 130 odd dwellings from VUEC. The average floor size was 12 square meters, which is what we've built these houses as, because people tend to have build small isolated rooms rather than one big house, often arranged around a central courtyard compound. So this room house is actually quite accurate in terms of size.
I just wonder if you would like to be able to share with us a bit of a lesson learned for you to work with universities across there in Africa. Is there any challenges, especially?
I think having Kate Goff on the team, who's done work with the University of Ghana for 30 odd years, has been great because she's smoothed the transition for me. It was probably difficult when we couldn't travel, but otherwise I'd recommend going over and seeing your colleagues as much as possible, so you can develop a relationship with them and communicate with them, because it's important to make sure everyone's on the same page. I think that's maybe one thing. Have lots of meetings with them. Otherwise, I found no issues working with other universities. We all have a WhatsApp group. We always keep in touch. So if there's any, especially when we're building these houses, if there's any questions, it was like we could answer almost immediately. I think just be responsive, work with good people.
So you mentioned in the beginning that people usually live in this one room house where they live, cook, sleep, and do all their activities.
Yeah, it depends where. So in Accra, because land is much more limited, that's what tends to happen. Up in Tamale, you'll probably have a compound of rooms of this size where they will have broadly different uses. But yes.
Prototype.
Yes.
My question is considering occupancy activities. So it's not only, as you mentioned, it's the body heat, body gain. So it's the occupancy activities.
Yes.
Is,
yes. So you.
Right. So for example, and for other activities, I think you have to consider.
Yes, absolutely. But the cooking tends to be done outdoors in most of these settlements we work with. But certainly, for example, a tailor or seamstress sometimes they have 4 or 5 irons on the go. You're right, that will increase the heat. And so I think your point was exactly the same. We should account for it, but purely for the means of comparing between different houses and identifying the effective interventions, it's best not to muddy the water. So for my PhD, I used UK homes and I synthetically occupied them. So I had light bulbs and things which produced heat. We could well do that here, but sometimes you just have to reduce the complexity, because obviously I'm not able to be there all the time managing the houses. So it's simpler just to have them all unoccupied. But your point is completely. Oh, in the simulations, yeah, exactly. So the plan will be to calibrate the models using the data we collect in these homes, and then add some internal gains. Yeah, it's a good point. Oh, great.
I'm just interested if language was an issue. For instance, for the WhatsApp diaries, because I know most people in informal settlement do not really speak much English. So I just wondered how to word it.
Yes. Well, so a lot of people were speaking into their phone and sending us voice clips, and then our local researchers were translating. Yes, and the community champions also translate for us when we go around. So that's a good point, because with the thermal comfort survey, the English questions of hot, cold sometimes don't translate across. So we had to be very careful with when we were doing the translations. And Arash will know this from Kenya and where else did you work? Nigeria. So you know the same thing. You have to be careful about the words you use and the meanings. We had a lot of confusion between humidity. So I was trying to say, do you feel humid? And we eventually, I think we settled on clammy or sticky. That was the word which people resonated with, understood.
So
Is the area affected by water shortage? Active metals? Are you guys planning maybe in the future? Because based on the climate, like for example, kind of water-based cooling,
Yeah.
would make a massive difference, but I don't know how much water is available.
In Accra, there tends to be there's a Volta River which runs through Ghana. Accra tends to be quite well supplied with water. Tamale has a few more issues. The problem with water-based cooling solutions, such as water on roofs, is that they become mosquito breeding grounds, and people are very worried about any kind of standing water for mosquito breeding, basically. So that's why we haven't looked at evaporative cooling and.
Yeah, I didn't mean like a phone or anything.
Okay.
Like, you know, like solar panels, they use that. You have just to buy. Black water, just flow them. And it can be immediately absorbed by the ground, so that you don't have.
Oh, okay,
So
okay.
you don't have a pond or anything.
Yeah.
Sometimes water flowing. And because the solar panels are that they overheat, right? So something like this could be very effective in places you don't need a drinking quality water, right? So
Yeah.
River or,
Yeah.
So I would just want, I recognize that that's the next step. The other question I was wondering, like, how much the night radiation cooling of the roof contributes to the whole story, because if it's not substantial, it's not that big of a loss, then you may want to consider a double layered roof, right?
Yeah.
It looks relatively, and it was metal, but it still looks relatively inexpensive. But if you have a double layer, your radiation gain would drop massively, right?
We have suggested a double skin roof, but people have mentioned the cost as an issue, because like building materials in Ghana in the last year have doubled in price.
Yeah, still I know everywhere.
It's really crazy.
Yeah.
It's something we thought about, and also the means of constructing a double skin roof. It's perhaps something we need to try in these test houses, show people, see if it becomes more acceptable through the demonstration.
Yeah, because like one thing, because it's like corrugated roof, right? So I recognize like having one layer of that base, there's another layer would be ideal, but it's expensive. But the other thing, actually, you could just take one layer of that, another layer, invert it, and then you have the air channels.
Yeah.
And that's like the structure is almost the same. You don't need spacer, save a lot of trouble. You eventually your same.
Yeah.
And it would give you it would actually be less effective, but it's make actually a difference. So that would be interesting to see how that would.
Yeah. Oh, we'll bear that in mind and see if we
But
can.
it's just exciting project.
Yeah. Oh, thanks.
Yeah, perhaps there's a PhD project there.
Yes.
Thank you for this wonderful. My question is about city selection.
Mhm.
I know that factor assembly is like 400 miles
Mhm.
from each other. Why did you select these two cities?
Because there was a pre-existing relationship with the University of Ghana, who are based in Accra. So that's their local, their local patch was Accra. And then at the start of UEC, they wanted to expand the team, and they said, "Oh, is there anyone we know who's good?" And he lived in Tamale. So it was a bit fortuitous. It was also because they were distinct, slightly distinct climatically. So it wasn't completely planned, but it worked out well. And so if we get the next grant that we apply for is also going to introduce Kumasi, which is the second largest city in the middle. And so they have sort of like a half Accra, half Tamale climate. So again, it's you someone who lived there. There's no more complicated than that.
Are you considering to study the effect of relative humidity as well? Because I think it will be like.
Yes. Yeah, so the one I showed you at the start, that was from VUEC, which was the first project. And in that project, they didn't measure relative humidity. So that's why they only had the temperature available. And then it was when we came in and joined the project in refit, we did the thermal comfort surveys and showed how important relative humidity was. Yes. So in the future, we're going to replace all the old sensors with sensors that combine temperature and humidity. But yeah, humidity is massively important for this kind of climate. Yeah.
Just a follow-up question on the design of these houses. I think one of the questions you answered, like you're going to propose some of the designs for adaptation, and I'm guessing it's probably for retrofitting.
Yes.
Because I was wondering, like 2 points. Like one is, I think Ghana is also working on a new building code for their country. I'm not sure whether it's implemented yet or not, but it to suggest building code or how to design new buildings, residential buildings. So I don't see like the options are very limited here, because all these 4 exposed walls were using the same materials.
Yeah.
So the exploration on that big chunk of option on in this project.
For this project, it was purely about retrofit, because it was kind of saying, well, the most vulnerable people are the people who can't afford to build a new house. They're the ones who are living in these kind of houses. But yeah, we toyed with the idea of doing new build in the new project that we've proposed. In the end, we again stuck with the retrofit. Yeah, you make good points about the limitations of the cells themselves. Yeah, so the new, as you said, the new building regulations, they were introduced in 2018, but they're being like changed all the time. Yeah, it'd be good if someone's interested in a project on new build, that'd be great.
I think I'm going to give Ben a bit of a break. I'm going to ask him one quick question, and then you're happy to hang around for tea and coffee, and if people want to stay and do more.
Got the room till past, haven't
you? Okay. But yeah, just ask, how did your time with the Lolo CDC prepare you for the work that you're doing now, and what the valuable lessons you learned during your time in the CDC that
That's a good
fed
question.
into the work that you do now?
Message and advice you have for the new students?
Yes. So they're already here. They're already signed up, so they can't leave now, can they? No. It was Lolo for me was it was my first introduction to engineering and building physics. I'd come from a geography, social science background, so it was like it completely opened my world up to all these exciting things that you can do to change the world. But yeah, Lolo and Irby likewise will give you all the skills you need to go on and be an independent researcher. As long as you just take every opportunity given to you, find a project you're interested in, and something that will keep you entertained for 3 or 4 years or 5 years potentially. Some of us. Well, yeah. Yeah, just I would say make the most of it. Yeah, really do everything you can. Be adaptable. If someone says, "Can you help me with this short-term project?" Do it, because that's how I got involved in the COVID project. Someone said to me, "Oh God, we need to set up all these sensors in these theatres and sports stadiums. Can you help out?" I said yes, and it's like changed the trajectory of my career. So yeah, always say yes, I would say.
Brilliant.
Well, you just don't tell them.
They're gonna find out.
All right, well, thank you again, Ben.
Oh yes, I'm sorry, yes. Sorry, Matt's got a little.
Just a quick couple of dates for the diary. So the BERG Seminar is a monthly series. So the next seminar, we're planning for it to be at the end of October, the last Wednesday of October on the 20th, on the 26th. Theme speakers to be announced. In a more general sense, if any of you have suggestions for themes or potential speakers for future seminars, please do get into touch with myself or with Vincenzo Rossi, who's also organising the seminars. And then the week after that, on Wednesday, the 2nd of November, is the first ABC Research Day, which is a student-led event exhibiting work from doctoral researchers and early career researchers. So they're currently taking submissions for posters and presentations, and registration can be done at the link there. To give a chance to see what work is done, not just in BERG, but across the whole school. And that's all. Yeah, just again to say a big thank you to Ben for his time today and for preparing for today. And thank you all for coming. Oh yeah, please do help us out to.
Oh, that's all right. I'm just going to stop the recording.
Please take some biscuits.